All right, so moving on and finishing up section 14.6. So we want to look at the impact of combining all of these things, the understanding the difference between how you polarize an insulator, polarize a conductor, and then how these fields impact matter. So we're going to do an example, and we're going to walk through it slowly just to make sure we understand the physics of what's going on. So let's say we have a metal ball and a plastic rod. All right, so what we're going to do is we're going to rub the left end of the plastic rod with fur and deposit electrons. So now the rod has a charge of 2 times 10 to the 9 electrons. Okay, so now if we go back to our drawing, we have our metal ball and our plastic rod, and we've deposited these electrons on one end. So what's going to happen is it's going to polarize the metal rod. So the positive charge nucleus is going to go towards the negative end, and the negative electron cloud is going to want to get away from that negative end. All right, so the plastic is an insulator. So the charge stays on the surface. So, and also this is going to end up attracting the metal ball. All right, so let's draw a couple fields. So, got our ball, we've got our charged rod with polarized atoms, and the ball is going to experience an electric field from the rod, and the electric field will be pointing towards the right because we have a negative charge here dictating that the field will point towards the negative end. All right, so if we look at the ball in a little more detail, so it's going to experience the force from the rod and it will get so we've got a force on the negative, and then the force on the positive charges, leading to a net force in this direction, which makes sense. The ball is going to want to go towards that negatively charged end. All right, so let me make this one bigger to further exaggerate it. So these are the force on these negative particles, and these are the force on the positive particles from this negatively charged end of the rod. All right, so what if we were to repeat this experiment with a metal rod. What then? Okay, so first of all, let's think about how the charge deposits. So we charge up our metal rod. So give electrons to the metal rod. And remember, these electrons are free to move. So what would happen is it would become negatively charged, but these charges would go directly towards the surface. This is a metal, and so the charge wants to go to the surface. And then we're going to have our ball over here. And the result of these negative charges is going to polarize that metal ball. So let's look at once again. This ball is going to experience a field from the rod, which once again will be pointing towards the rod. The negatives are going to have a force going in that direction, and there's going to be a force on the positives. So and what we can see is that the net force on the ball will be greater. And the reason for that is these charges are more spread out, and so you won't have quite so much repulsion. All right, so let's do an example. So the center of a small spherical ball of radius r equals 8.2 millimeters, carrying Q is equal to plus 3 times 10 to the minus 8 coulombs. This ball is at 14 centimeters from a copper wire of length equals 7 millimeters. We're going to calculate the force the ball exerts on the wire. All right, so if we draw this, we have our wire here, we have our ball here. They are located some distance r equals 14 centimeters. And then what's going to happen is the wire is going to polarize. So you'll have a positive end and a negative end. So Q plus and Q minus as a result of this positively charged ball. Now technically this ball is going to polarize as well, but the effect of this is going to be very, very tiny. All right, and so you're going to have attraction between these two objects. And so we know the magnitude of the force on the ball is going to be equal to the magnitude of the force on the wire. This is just due to reciprocity. And the force on the ball is equal to the charge of the ball times the electric field from the wire. Now, we don't know yet how to calculate the electric field of a wire, but we can definitely approximate this electric field, something that we already know. So we can say the electric field from the wire is approximately 1 over 4 pi epsilon naught 2ql over r cubed. So where did this come from? Well, we're modeling the wire as a dipole, which makes sense. We've got two ends of equal charge magnitude but opposite signs. All right, so we need to find the Q of this wire. Okay. So we've said the wire is polarized. And as we've already gone through, that would then imply that the net field is equal to 0, because polarization happens in equilibrium. So the field from the ball is equal and opposite to the field from the wire. So let's consider, so we've got E ball, E wire. So let's consider the center of the wire. So we've got plus Q over here, minus Q over here. It's length L. So if we're at the center, we've got L over 2, L over 2. And what we can do is we can model each end of the wire as points. So let's model So we're going to now move away from our dipole equation, and instead we're going to say E net is equal to E ball in X plus E positive end in X plus E negative end and in X. And we know E net is equal to 0, so this is just minus 1 over 4 pi epsilon naught Q over R squared plus 1 over 4 pi epsilon naught Q over L over 2 quantity squared plus 1 over 4 pi epsilon naught Q over L over 2 quantity squared. And so we have Q over R squared is equal to Q 1 over L over 2 squared plus 1 over L over 2 squared. All right. So Q over R squared is equal to Q times 2 over L over 2 squared. And so we want to solve for Q. So Q is approximately Q over 8 L over R squared. All right, so now we can use the force is approximately Q 1 over 4 pi epsilon naught 2QL over R cubed. It's approximately 1 over 4 pi epsilon naught Q squared over 4 L over R squared, L over R cubed is equal to 1 over 4 pi epsilon naught Q squared L cubed over 4R to the 5th, which would be what we would expect. And so Q is equal to 3 times 10 to the 8 coulombs divided by 8, 7 times 10 to the minus 3 meters divided by 24 times 10 to the minus 2 meters, quantity squared. Q is equal to 9.3. 8 times 10 to the minus 12 coulombs. This is why we didn't worry too much about how much that was going to polarize the ball. You could see that's a very tiny charge. It would barely polarize. And so we can plug that into our force equation as equal to 9 times 10 to the 9 Newton meters squared over Coulomb squared times 3 times 10 to the minus 8 coulombs squared, 7 times 10 to the minus 3 meters cubed over 4 times 14 times 10 to the minus 2 meters to the 5th, and this is equal to 1.29 times 10 to the minus 8 newtons. All right, and so for the end of chapter 14, just read the 2 remaining sections on your own. They're fairly conceptual, and the book does a really good job of explaining them, and that sums that up.